as you are familiar with the topic activation energy, that is the minimum energy which should be possessed by the reactants in order to cross the energy barrier or in order to cause effective collisions, or you can say that makes the reaction happen or progress. And so that means it increase the rate of reaction. Now we are coming to the point, that is we are going to talk about the kinetic energy. As you all know that all the reactant molecules possess some kind of energy, right? They have the kinetic energy in themselves. But what happens, like if we have a system in which there are so many reactants, all reactants do not possess same amount of energy, right? Some reactants have you can say more energy, and some reactants have less energy. And as you all know that like for the effective collision we need the effective collision, like for effective collision we need that the reactant should possess minimum energy corresponding to the activation energy. So that means only those reactant molecules which have got that energy equivalent to activation energy or more than activation energy is going to cause effective collision. Otherwise the molecules which have less energy are not going to have a more impact in the in the reaction, right? They will be colliding, but it won't be a effective collision. So that means what happens, so keep in mind that in a system, like in any system where you have reactants, all reactants do not have same amount of kinetic energy. Some are less energetic and some are more energetic, right? But we need the molecules which should be more energetic because they have more impact in in causing the effective collision other than the molecules which are less energetic. Then what happened, this kinetic energy concept was actually explained by Maxwell and Boltzmann by using the stats, right? So they just equated the fraction of molecules versus energy, and they just showed that what kind of molecules possess what kind of energy and which kind of molecules are going to cause effective collision and which kind of molecules are not going to cause effective collision. So just look here what we have. This I am plotting, I have fraction of molecules, and this is the energy on this x axis, right? So then what happens, just concentrate on this curve made of black, right, not the red one. So what happens, we see that if we correspond, then this is a peak, right? So that means the molecules which are present on this side are less energetic and the molecules which are present on this side are more energetic, right? And we know that but the you can say maximum number of molecules or the fraction of molecules which possess speed is actually the average speed. This is called as average kinetic energy. So that means there are only few molecules which possess have less energy, and there are only few molecules which have more energy, right? The molecules with less energy are going to have less impact in the chemical reaction, because we know that they should have energy corresponding to the activation energy, then only they can cause effective collision, right? And the molecules which are more energetic even are less, but they are going to have more impact in collision because they have energy greater than the activation energy. So when they will be colliding, they will be causing an effective collision. That means the breaking of bond and you can say formation of product, or you can say that it will increase the rate of reaction. Now, but most of the molecules which we see in a system possess energy corresponding to this. This is the average kinetic energy, right? But when we talk about the activation energy, it comes out to be, suppose this. So we say activation energy comes out to be this EA, right? And this is the energy which is possessed by maximum number of molecules, right? So that means the molecules which will possess at least energy equal to activation energy or more than activation energy is going to cause effective collision. And as we can see in this graph, there are only few molecules which are coming on this side. They have energy actually greater than the activation energy. So that means they will be causing effective collision, right? So that means out of total reactant molecules, the molecules may be colliding with each other, but the result is that they are not causing the effective collision. Only this part, you can say, only this fraction of molecules are going to cause effective collision because they have energy greater than the activation energy, right? Now what happens, as you all know that when we increase temperature, then the rate of reaction also increase. So what happens on increasing the temperature, we are going to see with this graph how Boltzmann and Maxwell explained it. They said that when we increase the temperature, then this is the graph which I have shown with the red line, right? So that means this graph just lowers down, and this is the average kinetic energy now. So that means now more you can say many of the reactant molecules have got the energy corresponding to this average kinetic energy, right? For example, if I say that suppose I am your teacher and I am just putting up some test for you and I say that passing marks are 30, right? If I make that passing marks 30, suppose 3 children pass, but if I reduce that marks from 30 to 20, that means I will get to have more student pass, right? So like when it was 30, suppose 3 students got secured passing marks. Suppose I reduce it to 20, suppose 5 got those passing marks. So that means on increasing the temperature in a similar manner, on increasing the temperature, this graph, this slope is just pushing down. That means now more the molecules are possessing the energy equivalent to average kinetic energy. And as we can see that this is the average kinetic energy. So that means these are less energetic and these are more energetic. Now when we talk about the molecules which are going to have more impact, then that means this much area, right? So that means this much area is now is going to have more impact in the the reaction. That means it is going to cause effective collision. So obviously the rate is increasing because the collision frequency which we get to see here is increasing because now more fraction of molecules have got the energy greater than the activation energy. So this is how the Maxwell and Boltzmann explained this graph. I think it's clear. It is just that we are plotting the fraction of molecules versus their kinetic energy, and what we get to see that the molecules with lesser energy are less and the molecules with more energy are even less, right? But you can say the fraction of molecules which have energy corresponding to the peak is maximum, which is called as average kinetic energy. But we know that for the reaction to happen, the reactant should have energy greater than activation energy. So all those molecules which have energy equivalent to activation energy or greater than activation energy are going to participate in a chemical reaction. That means they are going to cause effective collision, they are going to cause the reaction happen, or they are going to produce the product. That means they are going to affect the rate. But so this is the you can say, like when we talk about any system, this is the given condition, right? But when we increase the temperature, then what happens? The kinetic energy, average kinetic energy of molecules get increased. So that means we get to have more molecules which possess more activation energy. That means collision frequency is going to be more. That means the rate of reaction is going to be more. So this is what they explain in Maxwell-Boltzmann curve. Now we have a relation, like Arrhenius explained this whole thing with a mathematical expression, and that was K is equal to this. K is equal to E negative EA upon RT. Now in this equation, what does this signify? This signifies the number of molecules which have kinetic energy greater than activation energy. That means those molecules which are going to have more impact in the reaction, that means they are going to cause effective collision. This is constant, and this is, you know, that it is a rate constant. So this is this kind of graph we have for this thing. Just the Arrhenius concept to show the kinetic energy, as Maxwell-Boltzmann explained with the help of curve by using stats, Arrhenius explained with the help of mathematical equation, right? So this is what is the kinetic energy. Now as you all know that for the reaction to happen, collision is required, you know that, right? You know that the collision should be effective, and for effectiveness we need certain factors. You are all familiar with it. Now there is a theory for collision, that is the collision theory. We have one theory related to collision which just tells us that how the collision get affected by different factors. That is the collision theory, right? So what does collision theory explains actually? Collision theory explains that yes, it is correct that for the reaction to happen, collisions are required, right? And for the collisions, there should be an effective collision, it should not be ineffective collision. That means the collision should be successful one. That means it you can say is capable of breaking the bonds, or so that the new bonds can be formed, right? So that means for the successful collision, there are certain factors which actually affect the working of this thing, the collisions, right? Like what are those factors now? First factor is concentration, second factor is temperature, third is orientation, fourth is speed, and fifth, last but not least, it is catalyst, right? So we have different factors which affect the collision. One is the concentration. See, I am just explaining with an example. Suppose I have a container, like in this I have got 4 reactants suppose, and in this I have got many reactants. So in which beaker you will find more collisions? Obviously, more is the concentration, more is going to be the collision frequency. So that means concentration is directly proportional to the collisions. That means more is the concentration, more is going to be the collision frequency, and hence the rate of reaction is going to be more. Second factor is temperature. As you all know that kinetic energy is function of temperature. That means when we increase the temperature, the kinetic energy increase, and this you get to see in this graph also, like we were increasing the temperature, the fraction of molecule possessing the energy corresponding to this peak increased, right. So that means when the temperature is increased, that means kinetic energy is increased. When the kinetic energy is increased, that means they can collide with a, you can say a large speed, which will just result in an effective collision. That means the breaking of bonds and formation of new bond. This is what we need in a chemical reaction actually, right. So this happens when we just increase the temperature, the rate of reaction is obviously going to increase, because the unsuccessful collision is going to convert into the successful collision, right. Third is the orientation, right. Suppose I am just explaining you with with an example. Suppose again my reactant as cars. Suppose I have this car A and this is my car B, right. They are coming with greater speed, and they are coming, they are just facing each other, like one car is coming from this side and one car is coming from this side. As they possess more speed, that means when they are going to collide, they will just crash into each other, right. So that means it will lead to a greater loss. That means it will lead to more breakage. Suppose now if I have car A moving in this direction, and I have one more car B moving in this direction, right. So my car B is moving here and my car A is moving after this car B. Then what happens? They just collide. They just again crash into each other. So in which case do you think the breakage is going to be more? When they are coming face to face, or when they are just crashing into each other, like one car is you can say in front and the other is behind. So in which kind of thing you can see the more breakage? Obviously it is going to be more in when they are face to face, because the area of contact is going to be equal from both sides and equal bonds are going to break, right. So that means this is what the orientation which I want to explain for you for reactants. Suppose now I'll just explain you with the reactants. Suppose I have this thing, one reactant here and other reactant here. They are coming closer to each other and they just get crash into each other, right. Now I have one reactant here, right. Suppose I'll just explain you with this thing. Suppose I have one reactant here and one reactant here. They are just coming closer to each other and they are just getting crashed with each other. Now in the other case, what I have one reactant here and other is here. They are coming and they are just touching each other and they are moving apart. So in which of the two cases you found that the collision is going to be the better one? Obviously when they are just coming closer and you can say the collision is from the center line, right, then the collision is going to be effective. But in this case, when they are just coming like this and they are just touching each other and they are just separating, the collision is not going to be effective. The collision will occur, but the collision result is that it will not lead to much breakage, right. The bonds will not break up to that extent that happens when they just crashed when they were face to face. That means orientation is very important. That means orientation is something very important. So that means when the reactants are coming closer to each other, they should be properly oriented so that the collision can occur in an effective manner. Next is the speed. Now, as the speed you can just you can explain with the similar manner as we did with kinetic energy, because kinetic energy and speed is one of the same thing. That means when we are going to have the cars like these cars, if they are coming with greater speed, that means they are going to crash or bang into each other in an effective manner. But when they are coming at a slow speed, that means they will collide, but that will be a condition of ouch, as I told you, right. So they are going to bang, but this will create a condition of ouch, just touching each other. Next is the catalyst. Now what is the catalyst? Catalyst is actually you can say a substance which just affect the rate of reaction without undergoing any change. Again I am repeating it, write in your notebook. Catalyst is a substance or a chemical substance, you can say, which just affect the rate of reaction. It just affect the rate of reaction, means it can increase the rate of reaction or it can decrease the rate of reaction, right? But without going any change in itself, right? Neither the state is going to change for the catalyst, neither the amount of the the catalyst is going to be changed. It is going to remain as such as you used when you just started the reaction initially, right? It is going to be same. So it is just going to, you can say, affect the rate of chemical reaction. Now the question is that how it is going to increase the rate of chemical reaction. Look at this graph, what I have. See, just look at this black line first. So that means this is the reaction, this is the rate of reaction, the speed. So I'll write concentration with time, or you can say rate, right? So that means the reactants are getting consumed, the reaction reaches to the peak and then it decreases, right? Now what we get to see in case of the reaction which involves the catalyst, this you can see that this is again increasing the peak and then it decreases. So that means in this case the you can say the activation energy or the energy barrier is that this point A. But in case of catalyst, where the catalyst is used, the peak is A dash. So that means how catalysts affect the rate of reaction. Obviously what it is doing, it is just you can say lowering the energy barrier, or you can say it is just lowering the activation energy so that more and more molecules can cross the energy barrier to cause an effective collision. As I explained you with an example, suppose I am your teacher and I am conducting a test for you and I say that the test is of 100 marks, and if you will secure 50 marks and that 50 is going to be the passing marks, that means the student which will get marks at least 50 or more than 50 are going to pass in this exam, otherwise the rest of them are going to fail, right? Then what happens, suppose I just when I fixed the passing marks as 50, suppose 10 students out of class just passed that exam and the rest failed, right? But if I will reduce that 50 marks to 30 marks, then obviously the number of students that are going to pass will increase. In a similar manner, what a catalyst do, it just you can say lower the energy barrier, it just lower the passing marks, right? So that the activation energy is lower and more molecules can pass. Pass means they can you can say cross this energy barrier to cause effective collision, which is required to make reaction happen or to make product. So this is how catalysts affect the rate of reaction. So if somebody is going to ask you, or you're going to write in a technical form like this, that catalyst is a substance which increase the rate of reaction without undergoing any change in itself. Now the question comes how? Then you are going to answer, it just lowers the activation energy so that more and more molecules can cross the energy barrier in order to cause effective collision, or in order to make the reaction happen, or in order to increase the rate of reaction. This is how catalyst is affecting the rate of reaction. And moreover, you have to draw the graph also, because whenever you are explaining anything theoretically, if the reactions are involved, write the reactions. If some graphically explanation is there, then just explain it graphically, right? So this is how the catalysts affect the rate of reaction. Now catalysts not always increase the rate of reaction. There are few catalysts which just decrease the rate also. So we have inhibitors also, we have promoters also, right? So accordingly, according to the need of the reaction, we use the catalyst, that means the promoter or an inhibitor. And moreover, you know that if the successful collision, like if we have a chemical reaction in which there is no catalyst present, then out of 10 collisions, suppose we have molecules, again I am explaining, you listen to me carefully. Suppose we have molecules, they are colliding with each other, right? So suppose I say when they are colliding with each other, there 10 collisions occur, right? And out of that 10 collisions, only 2 are successful, suppose, right? But when I am going to use catalyst in that case, what is going to happen? Out of 10 collisions, 8 collisions, would you believe that 8 collisions are going